This is the second of 3 parts where we talk about the transport of water in xylem of plants. And this section will concern itself in particular with water potential and how that works. All right, so when we talk about the chemical potential of water, which is symbolized by the Greek character psi, what do we really mean? Well, water potential is the ability of water to do work. So when we think about water potential, we're thinking about what can water actually do in terms of moving things from place to place. So we can increase water potential in 3 different ways. We can heat it up, and you're familiar with this if you know anything about a steam engine. That's basically what we're doing there, is we are increasing the ability of water to do work by heating it up and creating steam. We can do with water the same thing we can do with anything else. We can increase its potential to do work simply by raising it to a higher height. So we can increase its potential energy. And the other thing that we can do with water is we can pressurize it. So anything we do to put water under pressure will increase its ability to do work, to move things from place to place. There are also ways that we can decrease water potential, decrease the ability of water's ability to do work, and it's basically the opposite of the way we can increase it. We can, instead of heating it, we can cool it, we can move it down from a higher height to a lower height, or we can simply decrease the pressure on the water. All of those things will decrease water potential. There is one other thing, though, a 4th thing that we can do to decrease water's potential that is different from the 3 that we can use to increase it. And this is adhesion. So when water sticks to a surface, it inhibits the water's movement. And by inhibiting its movement, we decrease its ability to do work. So anytime we add a solute to water, so when we're adding, for example, salt to water and dissolving it, we're decreasing its potential because more of the water molecules are now bound up with that solute, and that reduces the water's ability to move. You can also decrease it too by sticking to the surface of, say a test tube. The test tube is polar, and therefore it's hydrophilic, and the water molecules stick to it, and that decreases the water's ability to move inside of the test tube. Okay, so why do we care about psi, or water potential, at least in the context of moving water through the xylem of plants? Well, the first thing is that movement of water depends on differences in the value of psi in one point of the plant and another point in the plant. So what happens is water moves from regions of higher water potential to regions of lower water potential. And in plants, what this means is from areas that are less negative to areas that are more negative. So for example, you might start from an area that's negative 0.2 megapascals in potential to an area that's negative 1 megapascal. Okay, so you're moving from an area that has a lower negative number to a larger negative number. What really matters are the relative differences in psi, not the absolute values. Any difference potentially can cause movement of the water. And it doesn't matter whether any of the values are psi or positive or not. So the way that the plant ends up moving water is by changing the water potentials in different parts of its body. And we'll see how this happens in xylem. Now, the other thing to know is that cells, any cell, will always have a lower value of psi than distilled water because cells always have dissolved components. And remember, when you've got dissolved components, those dissolved components are going to be binding up the water and making it less able to do work. So cells always have lower values of psi than distilled water. Now when you put a plant cell in distilled water, just through osmosis, water will rush in and cause those cells to swell. But in the case of plant cells, the cells don't burst because they have a cell wall, which is made out of primarily cellulose, but also a component called lignin. Okay, now we need to get a little bit more complicated because psi is actually made up of 3 different components, which we can see here. So water potential psi is made up of a pressure potential, an osmotic potential, which is symbolized by this subscript pi, and what's called a matrix potential. So let's go through and think about what these are. So what is the pressure potential? Well, the pressure potential is just like what you already probably learned in your physics class. Pressure is force per unit area, and that's the same thing for a water pressure potential. And the pressure potential that you have in water at any one point in a plant is just the sum of all the physical pressures exerted on the water. So there's atmospheric pressure, there's this pressure that the cell wall exerts, there's turgor pressure and other things, and the net sum of all of those gives you the pressure potential of the water at that point in the cell. And we generally measure pressure in something called megapascals, but it could also be measured in bars or atmospheres. So, and these are the conversion rates here. Don't worry about them too much. I'm not going to get into them, but just so if you come across these, you'll see them. And by convention, what we say is pure water at 1 bar, in other words, approximately under 1 atmosphere, has a pressure potential of zero. And when I say pure water, I mean distilled pure water. So there's no solutes dissolved in that water at all. Okay. Now, we can have positive pressure potentials and we can have negative pressure potentials. You could have a positive pressure potential if you place water under some kind of hydrostatic pressure. So imagine, for example, the water that is in the plumbing in your dorm, for example, or wherever you happen to live. There's pressure, a positive pressure potential in there, and that's why when you open up a valve, like at a sink, the water comes rushing out because of that positive pressure potential. The water is pressing against the pipes in that case, and similarly with a plant, if it's got a positive pressure potential, the water will be pressing against the cell wall. You can have no pressure potential, like we talked about in pure water, and you can also have negative pressure potentials when the solution of water is under tension, okay? So, in other words, anytime you pull on the water like a rope, you're putting it under a negative pressure potential, and we refer to that negative pressure as tension in the water. Okay, now how strong are these cohesive forces that we talked about previously in water, the hydrogen bonding? Well, in theory anyway, the tensile strength of water could be up to 30 megapascals. In other words, you could put a negative pressure potential on that column of water of up to 30 megapascals. Now, well, how does that compare to what it would take to raise water, say, 100 meters? Well, in theory, again, these are under ideal circumstances when I say in theory, you'd only need a pressure differential, a negative pressure differential of about 3 megapascals to raise a thin column of water 100 meters. In other words, to raise a water column from the soil to the top of the tallest trees that are currently living on the planet. In theory, you could have trees up to, 10 times taller than that. So in theory, you could have trees that were an entire kilometer in height. But as a practical matter, that doesn't happen because there are flaws in the xylem, in the way that the xylem grows, that makes it impossible to actually put 30 megapascals of negative pressure potential on that column of water. So in practical matter, you're probably never going to get trees taller than about 100 to 150 meters.